made it easier.
I want to remind all the participants to please just have your first name and your last name initial.
Dr. Virani,
Yes, sir.
just to make sure, are you fine with us like interrupting in the middle of your presentation to ask questions, or should you wait until the end and ask them all?
Both is fine. We'll talk about that when we begin.
Yeah.
We're going to use an interactive app, but
All right.
this is for you guys. So questions
So,
are welcome and encouraged.
Yeah, we'll talk
Alright,
about that
thank
in 1 minute, okay? Good question. Are we almost there? Let's see, we're at 69, okay.
Big group.
Yes. So we should be about what, Barb, about 75? About 75? Including, including.
No, it's going to be a
us?
little bit more than that.
Okay,
I don't know how many of your TAs are here,
I haven't looked.
but it should be 72 participants plus.
Plus us. I just don't want it to be beeping while. Okay, well, I think we can kind of get started here. What do you think? Okay.
I think so.
All right, so I have a team that's going to introduce Dr. Shanil Virani, and that team is Sonal and Alex G. My team that is going to do the questions is going to be a little different. Okay, so you guys sent out a Google Doc for questions. Still monitor that Google Doc and please monitor the chat. But Dr. Virani is actually going to do an interactive question app here in a minute, and he's going to talk about that as well. Okay, so Sonal and Alex G, you're on.
Awesome, thank you. Hello, everyone. Today we're going to be hearing from Dr. Shanil Virani, a renowned scientist, author, educator, and advocate. Dr. Virani was the co-author of a photo book on light pollution and the loss of night known as The Daughter of the Stars. Dr. Virani passionately advocates and emphasizes the dangers of increased light pollution. To raise awareness, he even created Starry Nights events that highlight how we can reduce light pollution in our communities. Dr. Virani earned his 2 undergraduate degrees in honors physics and philosophy from the University of Waterloo. He then pursued graduate studies on supermassive black holes at Yale. In 2009, Dr. Virani was awarded the Chambliss Astronomy Achievement Medal for his exemplary research as a graduate student. In 2013, he was named the Solar System Ambassador by the Jet Propulsion Laboratory. You can find Dr. Virani on LinkedIn and listen to his podcast on SoundCloud and Spotify titled Our Island Universe. He created and hosts, quote, a weekly podcast that looks at all things space and how what goes on up there can affect what's going on down here.
With over 100 publications in astrophysics and X-ray studies, cited thousands of times, Dr. Virani has made important contributions to our understanding of the cosmic X-ray background and supermassive black holes. Dr. Virani continues to be a passionate voice in educating the public in science and astronomy, hoping to inspire the future generations through an understanding of the cosmos. He frequently gives public talks in schools, summer programs, and conferences to communicate the importance of studying space and astronomy. Today, Dr. Virani will be discussing the process of finding hidden populations of supermassive black holes. These cosmic objects have, for the most part, been obscured and hidden, but with the advent of X-ray and gamma-ray surveys utilizing the cosmic X-ray background, these populations may soon be uncovered.
It is a great honor to welcome Dr. Virani as part of the guest lecture series at SSB. We're so excited to hear from you, and thank you for being here today.
Wonderful. Excellent job, Sonal and Alex. Thank you for the warm welcome introduction. I'm going to try to do this. And can I get a thumbs up from the group if you can see my title slide and hear me well? Okay. So as was advertised, I'm going to talk to you about hidden populations of supermassive black holes. My first name is Shanil. It's pronounced exactly like the perfume, just spelt differently. And I don't have a number after my name like the perfume does. And as Sonal and Alex mentioned, I do host a podcast. It's called Our Island Universe. It's a play on words. You might know that Immanuel Kant, the great philosopher, when we were first looking at these fuzzy faint patches in the sky that we'll talk about, called these faint fuzzies, as we now know them as galaxies, as island universes. And island universe. But as you might know, we now exist in a universe where there's a lot of ideas that show or suggest that we might live in a multiverse. The idea that our universe is not the only one, but our universe has a lot of incredible wonder and things that we need to figure out. So I like that name, Our Island Universe. I encourage you to check it out. And you can find me on Twitter and Insta, where I'm pretty active on posting science-related news as Shanil V. Okay, with that introduction aside, I want to turn our attention to talking about these black holes. Let me move my menu bar here. And this is a joke from the New Yorker, which I love. And for much of the work in the history of black holes, this was the best argument. It's black, looks like a hole, I say it's a black hole. And that's changed. It's changed, this idea has changed over the last 2 decades. But because you're the next generation of astronomers, astrophysicists, I want to know what you know. So where we're going to do this is because we're not in a classroom and it's hard to do the Q&A with questions and hands up and having that kind of conversation, which is critical to doing science. We're going to use this app. So I'm stalling here because I hope you got your phone out and you can use your camera to either scan the QR code, or you can just go to the slido.com and enter that meeting ID number. Either of those approaches will take you to a website where there's a couple of questions I'm going to ask you, but there's also a tab called Q&A, and I encourage you to put questions on there. And we'll go through as many as we can at the end, but I'll spend the rest of the day answering every question that pops up on there, and that will be live for the next 3 days, so you'll get to see all the questions and you'll get to see my response. So without further ado, I'm going to open the first one. And I want you to tell me, what is a black hole? It's an open text box, and a great answer in science is, I don't know. You know, we often tell ourselves that, you know, we can figure everything out, and generally we can, but there's a lot of things we don't know. So I don't know, IDK, great answer. If you have an idea, tell me your idea. And I'll give you a few moments. What we have, something like 73, 74. So at some point, we'll stop. We'll make a word cloud here. What comes up? Not a white hole. I like that. If you've never seen a word cloud before, the way it works, it's one of the things one reason why I love doing it is that the most common answer gets a bigger font size. So the IDK, I don't know, means more than one person has responded, so it's the font size is bigger. Light can escape looks like is the second most popular answer. Question mark. It's black and it's a hole. Well, that's the New Yorker. Yep. You know, the idea of a black hole is somewhat pervasive now in our pop culture. We see it everywhere, and you can see a lot of these words coming back, right? Extremely strong gravity. I saw somewhere a rip in the fabric of space-time, rip in space-time. Strong gravity consumes matter and energy. So these are great observations. A massive object. Any idea where they might lurk in the universe? Are they distributed everywhere in a galaxy? Are they distributed everywhere in the universe? Do we find them in preferential locations? Any idea of where they might reside, these black holes? Where might they live? Center of galaxies. Okay, we're at 62. So I'll give you the last few seconds to get your answer in. Spaghettification. It's actually a physical term. If you think that's made up, that person is correct. Spaghettification is something you need to worry about if you venture too close to the event horizon, which we'll talk about. So that's a very definite issue. Okay, let's try this one. So I asked you, what is a black hole? How are they formed? So you might see them, you might know some of the physics of them, but how do they form? Supernovae, density, collapsed stars, big stars collapsing. So this is not a word cloud. So this, as you can see, is just open text because I wanted you to know what different ideas. Supernova, type 2 supernova. Okay, so you guys know there's a difference between the different types of supernovae. Stellar death, when stars collapse in on themselves. I don't know, great answer. Okay, you guys got a lot of good ideas here. This is wonderful. A dying star collapses under its own mass into a super dense point. Collapse of a star greater than 8 solar masses. Okay, now we're getting quantitative. Large collisions. Most of the answers relating to stars and the evolution of stars, stellar evolution of stars. Lots of good answers here. So we're going to explore this. I want to know what you think so that when I tell you what I know, we can see if we can reconcile these differences if we're on the same page. All right, so we seem to have paused there. Let's go to the next one. So these are good theoretical ideas. You've told me that black holes have different ways of forming, having to do with stars. Now, this is a little bit of a dated question because if we have a picture, yes, okay. Now, that picture is relatively recent. Yes, correct. It was done with the Event Horizon Telescope, something that the VLA, of course, is a part of and spans with various radio facilities around the world, gives us the diameter of the Earth, the effective diameter of the Earth, as a large radio dish, equivalent large radio dish, to be able to get the angular resolution. We'll talk about that, to be able to do that. Now, if we have a picture of one, and a lot of people, M87, okay, I was going to ask you, guys are on the ball today. Was that in our galaxy? Was that in some other galaxy? And of course, it was an M87. We'll talk about M87 and what that naming convention means. But a lot of yeses. I don't see any no's. Kind of, but there's error. Maybe in the Q&A you can explain that. Kind of, but there's error. The one in the middle of gravitational waves have been detected. Great, great. Lots of them. All right, one more. So are they esoteric? So yeah, cool, they exist. Who cares? Maybe they don't have an impact on the galaxy around them. Maybe they don't have an impact on the evolution of the universe. They are cool. Is that the only reason why we should study them? Is just because they're cool and interesting, which is a valid reason. But I'm asking, and I want you to think about, do they have larger consequences? Supermassive black holes are at the centers of galaxies. Pretty sure they have important implications in studying relativity and elementary particles. Yeah. Need to know the physics of black holes. Yeah. Something to do with gravity. Yeah. They're great tests of Einstein's general theory of general relativity. And as you probably know, gravitational waves are a consequence of GR, which we now have finally detected, and we can do this quite regularly now. You might have heard just this week of new exciting neutron star black hole collision that it detected. And we'll talk about that if there's time. I'll give you another 30 seconds to finish up. We like things that break our laws of physics. I love that answer. One reason why we keep testing GR, GR is more than 100 years old. It's passed every test that we can think of in the cosmos to use as a lab. There's not one observation I can tell you in the universe as of 12:15 Eastern time today that's in conflict with general relativity. Yet we know that our understanding is not complete. One of the potential fates of the universe ends with the complete darkness, except with black holes, and Hawking radiation will dwindle them down over time. So that's an idea from Hawking's Brief History of Time. If you read that book, he talks a little bit about the kind of evolution. These are great answers. This is why I love this one particular topic, because it really gets you thinking and making sure we understand what these words mean, the ideas mean, and how they may be implicated in what we do. All right, I think there's one more. I may have lied to you. Let's see if there's one more. Oh, that we did last. Okay, so let's go back now. So I'm going to switch to my presentation. And now we're going to try and answer your questions one by one of that list. Now, remember, there's that Q&A tab in Slido. So as questions come up, if you have questions already, by all means, continue to populate that field with your questions so we can answer them. And you'll see at the bottom left-hand corner, most of my slides, I'll always have the QR code. So if something happens with your tab with Slido, or you forget where to go, you can always just scan that QR code. All right, so where do we begin? So more than about 250 years ago, as you probably know, Galileo used the telescope on the night sky for the first time. He didn't invent the telescope. That's a misconception. In 1610, he took two small pieces of glass and he turned it to the cosmos for the first time. And in doing so, he provided us with the observational evidence for a sun-centered model. There were four observations, of course, that Galileo did that provided the irrefutable evidence, the smoking gun evidence, if you will, that the heliocentric model, the sun-centered model, was the correct idea for how our solar system, and at the time, the idea of a solar system was not known. So the universe was just everything you could see in the night sky. And that was what our ancestors thought for the longest time. And it's not because they were dumb. If you've studied Greek-Roman astronomy, you may have heard of Ptolemy's model, which is a model that Ptolemy added to, but comes to us from Aristotle, Aristotelian times. And it works. It worked for 1,500 years, an Earth-centered model. You might ask, well, what does work mean? Well, if you're an observational astronomer looking at the night sky, you see, of course, the wandering stars, which is what the word planets mean, moving with respect to the background sky. You see them moving. And if you want to know where it's going to be tomorrow or a week from now, a model can tell you that. And this geocentric, Earth-centered, Ptolemaic model with epicycles, circles on circles, just a fancy word meaning circles on circles, can predict that to the ability that your eye can measure positions. It wasn't until the telescope that all of this was changed. And the four pieces of observational evidence that you might know from your study of physics when you start your AP physics class, of course, is that Galileo looked at the moon and found craters and mountains on it. He looked at the sun. Galileo's mom apparently never told him to never look at the sun. Of course, I jest. Galileo's mom didn't know about telescopes. But Galileo didn't know the incredible power that the sun has, and especially when you use optics that can concentrate the light on your eye, it will damage them. So you never look at the sun, but Galileo did, and he found spots on the sun. We call them sunspots today, but that's evidence number two. He noticed that these 4 points of light, when he looked at Jupiter, the largest planet in our solar system, had these 4 points of light that from over the series of few weeks to almost 2 months in January 1610, when he started his experiment, that would seem to always move around Jupiter. That was a key observational point. For the first time, he had evidence showing that some objects were orbiting something else other than the Earth. And of course, we call these 4 moons. These 4 points were the 4 large moons of Jupiter. We call them the Galilean moons in his honor: Ganymede, Callisto, Io, and Europa. These 4 large Galilean moons. And of course, the last piece of evidence that Galileo furnished that forever sealed the coffin on this geocentric model is that he observed Venus going through its full set of phases, just like our moon does, in an Earth-centered model. And you could try this experiment. Draw the Earth at the center, put the moon in orbit around the Earth, and try and come up with Venus having the full set of phases that the Earth does. And it's hard to do. You can do it, of course, and that's why Ptolemy's model was quite successful. But it's almost impossible to get Venus having the full set of phases that he observed by just using a telescope. And so Galileo provided this telescope. And of course, the successive centuries after Galileo, we had a lot of people that would use better and better telescopes until we get to pictures like this, where these faint fuzzies that people saw in the 18th and 19th century could be resolved, meaning you can see detailed images of these beautiful spiral galaxies. You can see that there's even depth to this image. This is in the foreground. This is closer to us than the background because it's much further away. It's kind of the light is dimmed and blurred because of all that haze, but you can see these dust clouds. That's what you see in silhouette here. These are dark bands of gas and dust. These are the reservoirs from which the next generation of stars could form. You notice that there's a structure to it, right? There's something bright in the center, it looks like, but then all this material, most of it seems to be in this kind of like pancake disk, right? And that's why we call it these disk galaxies, because most of the matter that we see by light seems to be in this kind of disk-like structure. But you also notice that there's all this faint light. This, of course, is called the halo, the galaxy halo. But you see all kinds of clues that are telling you how galaxies form just by taking these kinds of observations. So this is interesting. The galaxies look beautiful. Of course, with the Hubble Space Telescope, we can even do better now. Here's a beautiful galaxy where not only, so we're looking now kind of top down where you can see the center. There's the center of the galaxy. Looks like to be a couple of bright pixels there. But then you see, just like in this picture where I was telling you that this disk is this reservoir of gas and dust from which the next generation of stars could form, all of these pink knots that you see here in this color, these pink knots, reddish knots, these are active sites of new stars turning on, being formed. And you see them. So they're exactly in that disk. And notice now that there's a spiral structure. It's a little hard to see in this edge-on view. You can certainly see it's a disk, but it's hard to tease out the spiral structure. Looking on it top down, you can see these beautiful spirals emanating out. And it looks like there's also a companion galaxy nearby that it might be interacting. In astronomy, when you just see images like this, you always have to be careful because remember, we're looking at a three-dimensional universe, but projected onto a plane. So you never know initially if this is in the foreground or in the background or at the same distance, roughly, as this galaxy, right? So you always have to be careful. Distances are notoriously hard to get in astronomy, but there's ways that we've now made great success in getting that. And we see this kind of interaction happening. This is a gorgeous image, which I like because this is probably what our Milky Way, our home in the cosmos, would look like. We can't see the Milky Way in this kind of detail because, of course, we reside within it. And I'll tell you our cosmic address later in the presentation. But we have now accumulated enough evidence to know the Milky Way is a spiral disk galaxy and is barred. What does that mean? Well, you can see there's a stellar bar, stars that seem to be elongated, stretched out in this direction, and these spiral arms seem to be coming out of them. Yet another clue. And so if you're looking at galaxies, trying to study how galaxies form, evolve, change with time, understanding these kinds of structures, spiral arms, bars, the blue gas, the blue light, excuse me, again, is telling you new stars that are turning on, that are forming. And we can talk about why young stars are preferentially blue, but you probably already know that, but we can certainly talk about it. Whereas stars around the bulge, the central part, tend to be red. That again tells you a clue about these galaxies. but we see all kinds of structure. And our best evidence today is the Milky Way is a spiral disk galaxy with a bar in it, and the sun is about 2/3 of the center, 2/3 away from the center of the Milky Way. So we don't live downtown Milky Way. We live in suburbia, in an arm, one arm like this, where we can look into the center, we can look up, of course, and we can look out. So this kind of question and these kinds of images continued into the early part of the 20th century. And here I've taken some images from something called the Palomar Sky Survey. Palomar is an observatory out in California, and it did a lot of great work. Palomar and Mount Wilson specifically. Mount Wilson is in Pasadena, just outside of Pasadena, California. And you might ask, well, why did we have large telescopes in Southern California? Because 100 years ago, California, specifically Los Angeles, wasn't the large light pollution basin that it is today. Back then, there was dark nights, and it was a great place on the edge of the Pacific to put large telescopes, and it made tremendous discoveries, which is what we're going to talk about here. And so this is M74, and I'll tell you what the names mean in a minute, but all I want to show you here is rather than showing you the sky as black, the sky now is white. And so this is just an inverted image where you can see a little bit more detail in terms of that spiral structure, these arms, the kind of diffuse gas and dust I was telling you are the reservoirs. And then these are large star clusters, globular clusters as well that are superimposed in them. M74. So there was a French astronomer who was interested in looking for comets, asteroids, those kinds of things that would move with respect to the sky. But as he was surveying his sky, there were all these faint fuzzies that he would see them. And it annoyed him because he was not looking for faint fuzzies. He was looking for comets and asteroids. So he said, I'm going to make a list of all these things that I keep finding that I don't care about, that are annoyance to me. And he made a list, and the astronomer's name, as you might guess, was Charles Messier. And this is the 74th object in his list. And most of them are galaxies. So M74, beautiful disk. M84, not M87, which some of you mentioned earlier. M84 looks dramatically different than M74. So we talked about just looking at images of galaxies, looking at their morphology, their shape, and how they appear to us. We can learn a lot about the dynamics. This doesn't look anything like that. And of course, in the 1920s, Edwin Hubble, for whom the Hubble Space Telescope is named after, came up with this idea of a galaxy classification system. It's mostly wrong because he missed most of the galaxies in the universe and coming up with that. And that's because even though the Mount Wilson telescope that he was using was the largest at the time, he was unable to see a lot of these faint, smaller galaxies, which are the most abundant, these irregular galaxies. It has just a mundane name, but most of the galaxies that we see are these kind of train wrecks, irregular types, not the beautiful spiral or elliptical. So this is an example of an elliptical galaxy. And as the name implies, it looks like an ellipse, right? Not a circle, maybe stretched in one direction, and you can measure these kind of axial ratios, and astronomers do to define something called the eccentricity or ellipticity of ellipticals to see how they change. But the most common thing you notice is there's no spiral disk. Moreover, if you look at the colors of elliptical galaxies, they tend to be red, not blue. Now remember, blue was a telltale sign of young stars turning on. That we see only red stars in ellipticals suggests that they may not have these reservoirs of gas and dust to produce the next generation of stars. So when I was your age, the term often used to describe ellipticals were red and dead. Red, because that's the star colors you see. Dead, because there's no reservoir, there's no material for new stars to form. Whereas spirals were star-forming galaxies, because again, you have that reservoir material there, and we see them happening. Okay, all of this is pretty self-explanatory, pretty good, right? We've got galaxies. We see two different kinds, predominantly circa 1920, with spirals and ellipticals. What's this? Notice it has a different name. So it's not M74, not M74 or 84. This is called 3C273. And these names, astronomers always give horrible names to objects. If you follow exoplanets and the discoveries of these exoplanet candidates, you know they always have these weird phone number names. Astronomy in circa early 20th century wasn't any different. 3C here refers to the third Cambridge catalog. Cambridge, the real one in England, not the fake one up in Massachusetts, where I spent 5 years as part of the science operations team for something called the Tron Director Observatory. I love using that line, the fake one, because it gets some people upset, but I think it's funny. So 3C273, the third Cambridge catalog, and it was a radio survey. So, and if you follow up those radio detections in the optical, you find an object like this that doesn't look like an elliptical, doesn't look like a spiral, and in fact, kind of looks like a star, doesn't it? If you look at that hard enough, it's hard to just look at that image and say it's something other than a star. But this ain't a star. And this troubled astronomers for a long time in the 1940s because we didn't know what it was. Now, around the time of the 1940s, there was a German-American scientist named Martin Schmidt. And looking up some of the history of the SSP, I learned, in fact, that Martin Schmidt, a Caltech astronomer, actually spoke to your predecessors 33 times between 1960 and 1980, I think was the time range. And Martin Schmidt was using the 100-inch telescope atop Mount Wilson. And he had the idea, well, instead of taking an image, what if I took a spectrum? And you'd know that if you take a prism and you put it in the window and sunlight falls on that prism, if you look against the wall, you'll see that white light is actually not white at all. It's made up of this rainbow of colors. You might have remembered that acronym, right? Or mnemonic, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, telling you how the colors are staggered in white light. And so if you take the light coming from the optical image, you can do the exact, for astrophysical sources, you can do the same thing. And so up here in the top is a very low signal to noise. So you can see it's very, very grainy. You can see bright features here, some faint features here, and then a whole lot of noise. So taking a spectrum and then looking for these kinds of emission lines is a telltale sign to try and figure out what they may be. How do we do that? Well, here's a lab spectrum. So you can go in the lab, and you might have done this in maybe in one of your science classes. You look through, you maybe use a gas discharge tube of helium or oxygen or neon, and you look at it with the prism and you see these bright lines. If you haven't done that experiment, it's a great, easy one to do, but you can do that in the lab, and you can find out that depending on the element, these lines appear at specific points in this wavelength spectrum. So the x-axis here, this horizontal axis, is wavelength, just the wavelength of light you're looking at. And you see there's a line here, a faint one here, doesn't seem to be much here. Here are 3 lines that has been identified at 486 nanometers. If you're unfamiliar with these units of nanometers, a nanometer is 10 to the minus 9 of a meter. So a very small fraction of a meter. So 486 nanometers, you can see 3 lines here. You can go and measure these things. The brilliant idea that Martin Schmidt had was, I see lines here. What if these 3 lines that I see in my observed spectrum are these 3 lines, but they're just shifted? And they're shifted. If I look at the wavelength, you might know that visible light, the part that of the electromagnetic spectrum that our eyes are sensitive to, runs roughly from about 400 nanometers to about 700 nanometers, right? That's that blue to red range. And you can see these lines are all systematically shifted towards the red. This is where the term red shifted comes from. It's by taking a look at the spectrum and seeing if there's a systematic shift. Now, this physics that's employed here is not complicated. You probably know the explanations. It's the Doppler effect. If you've heard a train approaching you, or a siren from an ambulance or a fire truck, or a police car approaching you, you know the pitch changes as it approaches and it recedes from you. As it approaches you, the light waves get compressed and we see a shift towards the blue. If the source is moving away from us, the waves get greater, spaced apart, and it gets shifted to the red. So his idea, Martin Schmidt's idea, that these were 3 lines, very low signal to noise, but consistent with, all 3 were consistent with the shift. And if you believe that these were Doppler shifted, having to do with motion, then you come to the conclusion that 3C273 is not only not a star, it's relatively far away compared to the Milky Way and its local environment of galaxies, and it's producing a prodigious amount of light. Almost 1 million to 1 billion times more than our Milky Way, right? So this was the first sign. And of course, Martin Schmidt, I love showing this picture, was actually put on the cover of Time magazine when this idea first surfaced. And it wasn't just 3C273. He actually was uncomfortable with the idea that these things were very far and producing a prodigious amount. It actually took him observing 2 or 3 objects to show that these things were consistently turning up before, of course, he published his paper. And Martin Schmidt now has this huge, enormous legacy because he coined the term quasar, or contributed to the studies of quasar. So this object here was initially called QSO, quasi-stellar object. Quasi-stellar object. Quasi because it's not a star. Star because it looks like a star, and of course object because it's an object we can see. And then quasar was the term given to these things that we see in the optical. Yes, it's confusing, and I'll try and explain how we get through the vocabulary in a moment. But the critical thing here to recognize is that we see these objects that don't look like spiral ellipticals, and Martin Schmidt, taking the spectrum, suggests that we're looking at galaxies very far away, but the light from the center dominates that kind of light that we see in a disk or an elliptical galaxy. So all we see is the central core of the galaxy, and it's producing a prodigious amount of radiation. And they're moving away from us. So what's a black hole? Well, you know that if I throw a ball, you throw a ball, it comes back. You throw something up, it comes back down to us. And that's because inevitably gravity from the Earth dominates the relative motion on the surface of the planet when we throw objects. And no matter how fast a baseball pitcher can throw a ball, they can't launch a rocket or launch that baseball into orbit. There's a certain speed an object needs to be able to beat gravity from the Earth, and that's about 10 kilometers per second. And we call that the escape speed. So if we launch things, and of course we can do that, that's how we launch rockets that send rovers to Mars, like Perseverance and Curiosity, or we send satellites to the other planets, either the interior or exterior planets. And of course, if we want to send satellites outside of our solar system, like Voyager 1 and Voyager 2, not only do we have to launch it with the escape velocity greater than the escape speed from Earth, we have to launch it with a speed greater than the escape speed of the sun. Otherwise, the sun's gravity will dominate it and bring Voyager 1, Voyager 2, Pioneer back to the sun. So that's how we're able to do that. But there is a theoretical idea here that there's a speed at which we can launch things and we can escape the pull of gravity. Black holes as an area of astronomy, about 100 years ago was more of a theoretical endeavor. Black holes are a natural consequence of Einstein's fields equations, meaning if you do look at stars, many of you said a black hole is a result of stellar evolution or massive stars collapsing. That's correct. And if you ask the question about our sun, what's the inevitable end fate of our sun? It's not to form a black hole. One of you said that black holes, due to stars, there's a mass limit to get black holes, and that's also correct. Our sun is not massive enough to form a black hole. Our sun, one solar mass, undergoes nuclear fusion in its core. That was an idea that you can imagine long dominated conversations amongst our ancestors. What powers the sun? And as you might imagine, ideas like fire, coal, other kinds of energy sources were explored. It was only about 100 years ago, that we finally figured out how our sun and stars like it work. And we now understand that's nuclear fusion, something called the proton-proton cycle, which is just a fancy way of saying hydrogen's converted to helium. And so that's what our sun does. All stars along something called the main sequence, which you might have already learned about or maybe studying about, are undergoing nuclear fusion where they convert hydrogen to helium in its core. But when stars run out of that hydrogen, then gravity starts again wanting to compress it. You can think of a star as just a competition between the radiation it produces in its core, pushing out, and gravity, because of the large mass these stars have, wanting to compress it, wanting to smash it in. And while stars are undergoing nuclear fusion, they're in this kind of hydrostatic equilibrium. Hydrostatic is just a fancy word, just meaning it's in balance, right? But once that nuclear source turns off, gravity is going to want to crunch it. It's going to want to smash it. And so what happens for stars like our sun is that you can have something called a white dwarf, which is a faint ember of a star whose long-term fate is to fade away to darkness over cosmic time. So not terribly romantic, not terribly exciting, but it's not massive enough to compress it to form a black hole. It will form a white dwarf and will just fade away over cosmic time. Stars about 3 solar masses, so 3 times the sun's mass and higher, up to about 10, can form something called neutron stars, where the electrons and protons get smashed together to form neutrons. And that pressure from neutrons, from all the neutrons that it forms, is sufficient to balance gravity, and we can have neutron stars that are formed. But as one of you said, at some point, the mass is big enough that nothing can prevent the monolithic collapse to the center and a black hole is formed. That number is somewhat uncertain. We don't know exactly the number. The range is about 7 to 10 solar masses. 8 is a great number. If you just want to remember 10, that's an order of magnitude, that works too. So stars greater than about 10 times the mass of the sun, its inevitable fate is to form a black hole. Stars of solar mass, or a few times solar mass, is a white dwarf. In astrophysics, mass governs destiny. You tell me the mass of the star, and because the physics now is so well known, so well understood, I can tell you the fate of that star. But this is still a theoretical exercise, right? We're just looking at equations on the blackboard or the whiteboard. We're looking at consequence of what these equations mean. Maybe the equations are wrong. Maybe there's a different model that will tell us that that the things that we're exploring within the context of GR might not be right. This still doesn't tell you that black holes exist or should exist, and or that we can find them. And as a scientist, your role, your job, of course, is to always be skeptical, right? Is always to say, what does the evidence say? What does the evidence say? And as you know, what makes science and the scientific method so powerful is that it's not just the explanation you come up with to understand a phenomenon that's important. It's that your explanation makes predictions, right? That you, I, someone else can go out and test. And testing is a critical part of science, because either we can corroborate that the idea is consistent with what we see, or we can falsify it, show it's inconsistent. And no matter how elegant your idea may be, if it's inconsistent, the observations are inconsistent with your model, with your story, with your narrative, it's thrown in the wastebasket. We go back to the drawing board and we try again. So keep your skeptical hats on. All I've told you so far is that we have these different kinds of galaxies, and there seems to be a subset of which that have these bright cores that produce a prodigious amount of light. I haven't told you anything else about it. You may make the inference that black holes, of course, are somehow related, but it's not evidence, not proof to you that these mean black holes exist. I'm just saying that they're consistent with the idea. Okay, so there's all kinds of historical context, which is often very frustrating for new scientists like you trying to get in the field with different names. So that's why I intentionally try to omit all these names. You'll see them in the press, in the literature too. Quasars, quasi-stellar objects. Remember QSOs, Seyfert 1s and 2s. Seyfert was an astronomer. Carl Seyfert was his name, and he was studying not the 3C273 kind of objects. He was looking at spiral galaxies that seem to have brighter cores, brighter bulges than other spirals, and he was curious why these spirals had brighter bulges, and he found that by looking at the spectrum, he could break them into 2 types, type 1 and type 2. So again, this is historical context. They have these weird names like LINERs, which is another acronym, low ionization nuclear emission region sources, weird names. Blazars, BLAC, radio galaxies, whole zoo of different names. The way to think of it today in this modern context is to think of it as active galactic nuclei, or AGN, as it's abbreviated for short. And the model that has emerged over the last 30, 40 years is that in the center of galaxies, and we think all galaxies now, is you do have a supermassive black hole that lurks at the center. How it got there, how it gets so big, why some are active, meaning they're actively devouring material, why most appear to be dormant, they're not devouring material. These are outstanding questions in astrophysics today. To what extent do these central black holes play in the evolution of galaxies over time? Another critical question. If you're a galactic astrophysicist, you're interested in galaxies and what they tell us about cosmic evolution, you need to understand the interplay between the central supermassive black hole and the galaxies they reside in. And surprisingly, there is a connection. You might not think that, and I'll show you some of the evidence for why we think there is, but this is the idea. So you have the central black hole at the center. Around it is this reservoir of gas and dust. Now, depending on how we see it, so this has a version where we're seeing this cartoon shows us kind of edge on. So the black hole, so here's the black hole right at the center, and the disk is in front of it. I don't get to see the black hole, right? It's obscured by this donut of material. The donut idea is called a torus, which means you kind of have a cylinder with a hole in the middle where the black hole resides, but this donut, this torus, is sufficiently thick enough to block the emission. Not all of it, as I'll tell you in a moment, but at least in the optical, you don't see the evidence for the supermassive black hole. These BL-LAC objects, the way these things come into play is there are some galaxies, particularly when we look in the radio part of the electromagnetic spectrum, where we see these long extended jets coming out from the core. They're called radio jets, and how these jets are produced, what they're made up of. We think they're electrons following magnetic field lines, right? But these are still questions in modern day astrophysics. Collimated, meaning how straight these jets are, is another big question. How do they stay collimated? How do they stay linear for long, enormous distances? We still are trying to figure that out. In fact, radio facilities like the VLA have been a real game changer in understanding the dynamics of jets and their connection to radio galaxies. But the key thing here is a zoo of objects is better to think of as, rather than these historical names, just think of them as AGN, active galactic nuclei. And the model, with no evidence I've told you, but the model seems to suggest that there's a central supermassive black hole. And it's important that central and supermassive stay in your mind, because central tells you where they're preferentially located. I asked you that. These supermassive galaxies aren't uniformly distributed in a galaxy. In fact, they're at the center. So that's a clue telling us somehow, why did they get to the center? Were they always there? Did they move there, right? Those are great questions. How do they grow so big? I've told you supermassive. Astronomers are great with coming up with describing words, right? The universe was created not just in an explosion, it was a big bang, right? We're building telescopes larger than the 100-inch telescope in Mount Wilson in Chile, right? In the Atacama Desert, also in Hawaii, right? And they're big. How big? Well, they're very big. So we call it the Very Large Telescope or the Extremely Large Telescope, right? We come up with these great words. So supermassive doesn't really tell you how big they are. The supermassive black hole in M87 is 1 billion times the mass of our sun. The supermassive black hole that we think lurks at the center of our own Milky Way galaxy is about 4 million times the mass of the sun. So that tells you some sense of how big they are and what supermassive means. Okay, so the question you really are thinking, how do we really know they're there? You know, that New Yorker explanation, they're round and they're black, so it's a black hole, doesn't work in science, right? So how do we know that they're truly there? And what's the evidence for them to exist? Now, a lot of you said that we know that black holes could form as a result of stellar evolution, and that's this picture. So you guys were absolutely right. We talked about these reservoirs, these gas and dust lanes that you see in spiral galaxies, and that's how we think our own solar system formed. There had to be a trigger event, something that caused a large cloud of gas and dust to collapse inward on itself. And the most likely scenario for that collapse is usually a supernova. So a massive star nearby that's exploded, and the wind, the pressure from the explosion can hit the gas cloud and cause it to fall in. And that likely is step 0 in any recipe to form a star and its family of planets and maybe life on it, is that you have these reservoirs of gas and cloud, some kind of explosion, a supernova explosion may cause the gas and dust to collapse. And when it does, physics takes over. It's really a consequence of conservation of energy, conservation of angular momentum, and then nuclear fusion taking off in its core. The end inevitable result, given a mass enough cloud, is a star to form. So we talked a little bit about this. I'm just going to fill in the details now. A star turns on, really becomes a true star when it starts igniting nuclear fusion in its core, right? And we talked about the main sequence as being when stars convert that hydrogen into helium. The proton-proton cycle. And so when stars are doing that part, where they spend most of their lives, in fact, is in that phase. We call it the main sequence. But as they evolve and they deplete the amount of gas in its center to burn, so it goes from hydrogen to helium, that's the main sequence. But then for our sun, it will have exhausted its hydrogen supply for the most part. It will then start a CNO cycle, carbon, nitrogen, oxygen. And this will continue all the way up to iron in the periodic table. You might remember those terms endothermic and exothermic. Remember those terms from your high school chemistry class, right? And that's, you might ask, well, why does it stop at iron? In every one of these reactions, I haven't said it so far, but your intuition might be telling you the reason why these reactions, in the case here, the hydrogen to helium is so important is because if you use Einstein's equation, E equals mc squared, and you measure the mass of a hydrogen atom multiplied by 4, because it takes 4 hydrogen atoms to make 1 helium atom, and then you go and look up the mass of a helium atom in your periodic table, you'll recognize that 4 times hydrogen doesn't equal helium. There's a small mass deficiency, small mass difference. And of course, that tiny amount of mass difference is converted into energy. And because it's E equals mc squared, it's the speed of light, c is the speed of light, and you're squaring it, you only need a small amount of mass converted into energy to produce, or excuse me, small amount of mass, small amount of mass to be converted into energy to produce the light and the electromagnetic radiation received from our sun and from other stars. So that's E equals mc squared. To convert the hydrogen to helium, that energy is liberated, so it's exothermic, right? When you get beyond iron in the periodic table, energy becomes an input. You need energy to produce elements heavier than iron. Well, that's not going to work for sustaining stars now because we need the energy to be liberated to balance gravity. Now, you might ask, well, the periodic table has elements beyond iron, so they must be formed. And that's correct, but it's not in the cores. It turns out to be in the winds and in the later stages of stellar evolution. In fact, that's still an area of astrophysics that's being explored and understood, how we get the periodic table, the full periodic table that we see in your chemistry high school's class. You might know, of course, that the first 3 elements, hydrogen, helium, and lithium, were produced in the first 3 minutes after the Big Bang. That's when the conditions in the early universe mimic the conditions in the centers of stars, the pressures, the densities, and the temperatures high enough that all of the hydrogen, helium, and lithium we see was produced then. In fact, that's one of the pieces of evidence for the Big Bang, is that you can go and look at the amount of hydrogen, helium, and lithium we see, and it's exactly in concert, consistent with the predictions you would expect from a Big Bang and the conditions like that. That's one of the pieces of evidence. There, of course, there are several multiple independent lines of evidence that tell us that there was a Big Bang that created it. Some of you said type 2 supernova. So, and that's true. It's the massive stars that explode are the type 2. Now, what are type 1? Type 1 is like our sun, the white dwarf, that may have a companion star nearby that it's accreting. It's pulling matter away from this companion star. And if it pulls enough, it can have nuclear fusion take place in the outer part, and that nuclear fusion could cause an explosion and to have an explosion. And that's the type 1 supernovae, having to do with white dwarfs accreting stellar material. Type 2 are the massive stars. So for now, don't worry about the distinction between type 1 and type 2. Just for this cartoon, recognize that it's the massive stars. And then we talked about these endpoints. There should be a third arrow for white dwarf. We ignored our sun altogether. That's not fair. But of course, the 2 bigger parts, the 2 main modes are here, are a black hole, a neutron star. So this is all to tell you that there is a mechanism to produce black holes, but it doesn't tell you they exist. So what do we see from observations? The Hubble Space Telescope was a pivotal part to the story, right? It was the Hubble Space Telescope that was launched in 1990, still operating. It's been shut down since the middle of June because it has an anomaly it's trying to work, and hopefully it'll be solved and it'll go back to doing science, the wonderful science it has been doing. But for 30 years, has revolutionized our understanding of all different areas of astrophysics. And so here, let's start with the left-hand picture. Here, there's a ground-based image taken from just any large optical telescope, again, showing you the light from the stars. But if you go and look at it in the radio, like with the VLA, here are those beautiful, large, extended radio jets coming out from the core, or coming out from the center. We can zoom in the center of this. We can only do this with nearby galaxies, so we have the resolution, the ability to look at it. And if you look at it in the center, this kind of looks like that cartoon I showed you, doesn't it? Right? In this case, this thing is tilted just a little bit with respect to our line of sight. There seems to be a few pixels showing a bright central core. We see this diminution of light consistent with a torus that's obscuring light. And then we see a lot of other light in the center. So this torus with the central black hole, this is not conclusive. It doesn't tell you it must be. It just says it's consistent with this idea. Now that's one. Here's another one. So this is another image taken with the HST. NGC is New Galactic Catalog. Again, another survey that astronomers did. And so here's the optical image where you can see this extended light. Looks like a nice spiral galaxy, but further away. But look how bright the core is. And when we look at it with HST, this is more a lot kind of edge on. So maybe there's a pixel, maybe 2 pixels. But again, like in that spiral galaxy where I showed you, where the side closest to us, we see the silhouette of obscuring material. And then, of course, on the far side, which is further away from us, gets dimmed away. Again, consistent with these ideas. But it doesn't tell you that it must be a black hole. Theoretical physicists are very clever, very smart. And for much of the discussion of the last 100 years, they came up with all kinds of different possibilities, right? Different other things that could be going on to explain these observations I showed you. So it doesn't necessarily imply the existence of a supermassive black hole. It's just consistent with that picture. M87, this is probably the textbook case now, of course, because of some of you might know about the picture, but look at this jet, right? You might ask, well, where's the other one? Well, again, this line of sight may be such that it's blocked because of the angle towards us, so we don't see it. So we see this one-sided jet. It doesn't mean there's only one jet. There's probably 2 jets that are on either side. It's just that the way it's been dimmed because of its orientation. Whereas this near side, we can see it very bright. Look how long it is. Look how extended it is. Remember I was telling you about that collimation, how it keeps that straight feature? How did the magnetic fields extend so far out? You know, how are these electrons that are spiraling around these magnetic field lines continue to do this for these large distances? If you figure out, tell me, because we're still trying to figure a lot of this out. Beautiful, beautiful radio jet. Remember M87, some of you already know why I'm showing M87 here. Now, the biggest way to figure out, to think, how can I conclusively demonstrate to the skeptics within the community, within science, that it has to be a black hole, we can do that by looking at the dynamics or the kinematic motion of stars. And this, while it sounds complicated, isn't. It's something you all know very well. And in fact, the mathematics that you need to apply to our own galaxy and to the old black hole is 16th century physics. It's Keplerian physics. If you look in our own solar system, right, Mercury whizzes around the sun, takes about 88 days to complete one orbit, one trip around the sun. Venus, the second planet, hottest planet in the solar system, but the second planet out from the sun, takes about 246 days. Of course, our year is exactly 365 and a little bit, and corresponds to the length of time it takes the Earth to make one trip around the sun. Mars a little bit longer, and of course, as you get out to Pluto, you can see the trend. It's not a line. It's not a straight line with some kind of constant slope. In fact, it's a curve, right? It's a Keplerian decline, and we can quantify that, and I'll leave that for you. But you see this in our own solar system, meaning that maybe if we looked at the center of our own Milky Way, we can find tracers that we can follow, and we can measure how its distance from the center, how long it takes to make an orbit, and we can apply these ideas of Kepler's. Kepler's third law, you might remember, describes the relationship between the period and its semi-major axis, how far away it is. And you can do this experiment. You can do the calculation. I'm going to show it to you now. So before I play this little clip, here I want to set it up. So Andrea Ghez is an astronomer at UCLA, University of California, Los Angeles. And when she came on to the faculty at UCLA, the Keck telescope, these 2 twin 10-meter class telescopes had just been constructed, had just been built atop Mauna Kea in Hawaii. And at that time, it was only astronomers within the University of California system that could get time. It wasn't open to the entire astronomical community. And Andrea Ghez, as a new faculty at UCLA, came up with this great idea. She said, I want to look at the center of our own galaxy, the center of the Milky Way, and I want to look at it frequently, every so often, and I want to do this for a long time, for years to decades. Because she argued, if we can find stars, so when you see these weird names, SO2, SO1, SO49, and it looks like this is a Photoshop, some kind of cartoon, when I play it, recognize this isn't a cartoon. The colors, of course, and shapes have been exaggerated, but what you're going to see are the exact motion, these stars that she and her team at UCLA have been monitoring. I'm going to move my title, my photos bar, so you guys can see the time. So in the upper right is the clock that starts in 1995, halfway through 1995. That's what the decimal 5 means. And then this error bar tells you the angular width, the angular separation. So this is 2/10 of an arc second. You might not know that in astronomy, we use angular measurement. And the way to kind of think about that is, if I extend my hand and I look at the angular separation between my thumb and my pinky on the sky, that's about 15 degrees. So I look at the full moon, that's about half a degree, right? And just like there are 60 minutes in an hour, there are 60 arc minutes in 1 degree, and there are 60 arc seconds in 1 arc minute. So 3,600 arc seconds in 1 degree. So this is telling you how small. Remember, full moon, half a degree, 30 arc minutes. This is 2/10 of an arc second, right? So very, very, very small. But this is the homework for those of you who want to try. You can think of the size, 2/10 of an arc second. The clock will end circa 2020. So you know the semi-major axis roughly, it's about 2/10 of an arc second. The period, about 25 years. From that, you can back out a mass. But watch what she's discovered. Pay attention to SO2, this star here. So this white star in the image doesn't correspond to anything you can see with your eye. There's nothing that you can see with your eye. But it's the dynamical center. I'm going to let it loop. So just look at the clock, 2012, 2013, 14, 15, 16, 17, 18, 19, 20, and then it stops. I'm going to play it again. That's not what I wanted to do. Look at SO2. And you can see there's another star. See if you can spot it. That seems to also make a closed orbit. SO2 definitely makes a closed orbit. So this is the one if you want to do the homework exercise, right? This length, not too dissimilar from 0.24 arc seconds. I keep rounding it to 2/10 of an arc second, and then there's your clock. This star is orbiting the center, about which we don't see anything special. What is going on? What is it that it's orbiting? This was the first smoking gun evidence for the supermassive black hole. Andrea Ghez, using Kepler's law, Kepler's third law, this angular measurement, this time, figured out a mass. You can do the calculation. You can look up the paper, but don't look it up because you can do this. Trust me, you can do this. It's not, there's a couple of units conversions, but you can do this. You'll figure out that the central massive dark object, which is what she and her team called it because they didn't want to necessarily assume it's a black hole. They just said this massive dark object that this star and another star, SO16, seems to orbit, weighs 4 million times the mass of the sun. 4 million times the mass of the sun. Remember, the sun, the solar mass is 2 × 10⁻30 kilograms, right? This is 4 million times the mass of the sun in a volume of space no bigger, roughly, than the size of our solar system. In our solar system, we have one star, the sun, weighs 2 × 10⁻30 kilograms. Downtown Milky Way, you have an object that weighs 4 million times the mass of the sun in a volume of space roughly the size of our solar system. That is the evidence that theoretical physicists had to agree and accept there isn't an alternative for what could be in the center other than a black hole. Now, of course, this was then added to by this gorgeous image that was released a few years ago that had simultaneous press conferences around the world. Astronomers at astronomy meetings, of course, had been whispering to each other and having these hallway conversations about the Event Horizon Telescope, whether they could see the center, whether they were able to process the image to process the data to make a gorgeous image. And what surprised astronomers, for one, surprised me, is that they didn't present the evidence from the center of our galaxy. They looked at M87, that large radio galaxy, with a large galaxy with that beautiful radio jet coming out. And when they did, they were able to produce an image like this. And they had press conferences, of course, in DC, our nation's capital. They had press conferences in Chile, where we had other radio dishes, and of course in Europe. And the fact that there was an email sent about an upcoming press conference in the nation's capital and around the world was a clue to all astronomers. Oh, this is a big deal. This is big news. And it's the event horizon. They have an image of the black hole. And this is why we all tuned in. Gorgeous image. And I hope you saw it as well. Some of you did. And of course, here's a little movie showing the data cut in time. So this obscuring material is dynamically changing. You can see it changing with time. This is in 2017. And of course, earlier this year, you might have seen another paper where they looked at the polarization of light. So how much the electromagnetic radiation is responding to the environment around it. And there was more science coming forward. Of course, the Event Horizon Telescope is not done. They're adding more nodes, more facilities to their structure. And of course, they have yet to release the data they've accumulated for the center of our galaxy. And of course, the reason why you might ask, well, how come they haven't released that, is that it's much more complicated because it's much closer and requires more processing and more interpretation before they do that. But that will come. That will soon come. So this two pieces are really the smoking gun evidence for why supermassive black holes exist. And recognize it's only the last few years, right? The last decade or so that we've got the evidence. It's in your lifetime. And as you might know, Andrea Ghez, and here's a picture of her with her medal, was one of the recipients. Reinhard Genzel is a European astronomer, and he was doing an equivalent survey that Andrea Ghez was doing. Andrea Ghez was using the Keck telescope, remember atop Mauna Kea in Hawaii. Reinhard Genzel was using the VLT, the Very Large Telescope, that the Europeans have access to. So they're very similar in characteristics, same kind of survey, getting the consistent results. And you might say, well, what's the point in duplicating, right? Science requires that we go out and not only do the experiment, but we find that other people get the same results. So it's wonderful to see two different experiments, two different people arriving at the same conclusion, and therefore the leaders of both of those teams were the recipients, Reinhard Genzel, Andrea Ghez. Roger Penrose, whom you might know, was a former colleague of Stephen Hawking, did a lot of fundamental theoretical work. So he was another recipient of the Nobel Prize in 2020. For Shanil and the other female astronomers on this call, the other reason why I wanted to show this picture is that unfortunately, we still have a lot of barriers in who gets to do science, who gets to do physics. It's becoming less so, and it's wonderful to see the fact that the diversity on this phone call showing you that it's not true for the current generation, but for my generation and my predecessors, it tended to be male dominated and had to do with the function of the climate created and not allowing women to make contributions. It's not that women didn't make contributions. Andrea Ghez was only the fourth female to win the prize in physics. But if you look at it in terms of the last few years, she's the second in the last 3 years. Second female in the last 3 years. We'll find out later this fall if there'll be another female recipient of the physics prize. But Donna Strickland won the 2018 prize, and she actually was at my alma mater, University of Waterloo, just south of Toronto. She was the third. You might know the first one. I'm sure you know the first one, right? Marie Curie. She won the first Nobel Prize, and then Geppert Meyer, who understood the electron or the nuclear shell structure for atoms, was the second Nobel Prize winner in physics. The thing I don't want you to conclude is that there have only been four female seminal contributions. There have only been seminal contributions for four female astronomers. That is not true. They just have not been recognized. You might know the story of Harvard computers, which aren't literal computers. They were actually the staff, at the Harvard College Observatory that were doing the painstaking work looking at those digital plates. I showed you an example from the Palomar, but there was the Mount Wilson Digital Sky Survey. They were the ones that were doing the painstaking work analyzing these images. In fact, it was Henrietta Leavitt that provided the relationship between the period and luminosity of a particular kind of variable star that fluctuates in brightness with the well-known periodicity called the period luminosity relationship, Henrietta Leavitt. And that was the critical piece that Edwin Hubble required to show that the universe is expanding. Without Henrietta Leavitt, you don't get Hubble's result. Henrietta Leavitt was never awarded the Nobel Prize. I told you that it's only the last 100 years that we figured out how stars work, and that it's mostly hydrogen at its core. That was Cecilia Payne-Gaposchkin in 1925. She wrote a PhD thesis at Harvard. One astronomer, Otto Struve, a very, very well-known astronomer historically, said it's probably the most brilliant PhD dissertation written in astronomy. Her conclusion was stars are mostly hydrogen, converting hydrogen to helium. She accepted a postdoc, which is a short research project you do after getting your PhD at Princeton, where she went and was discouraged from publishing her papers because it was thought to be not correct. And in fact, her PhD, her postdoc advisor was Henry Norris of the famed the Hertzsprung-Russell diagram. And he and collaborators shortly wrote a paper when he read her dissertation suggesting that stars are made up mostly of hydrogen. He cited her work, but she was never awarded. So if you remember two names, historical names, remember those two, Henrietta Leavitt and Cecilia Payne-Gaposchkin. Those are two names I think every student in science should know because they provided the seminal work that allowed astrophysics to continue. And I hope the fact that two of the last three recipients have been female tells us that we're making progress in making science open and inclusive to everyone. Okay, so I'll get off my soapbox. All right, so I've told you that black holes are there, that they exist, but how do you find something that's black? When the sky is black, how do you find them? This becomes incredibly difficult to do. We had to use circumstantial lines, like I told you with Hubble Space Telescope imagery, showing us that some semblance between the cartoon. Of course, Andrea Ghez works as a smoking gun, telling us that there is an object, but how do we find them in larger numbers to be able to do systematic studies, to be able to understand the relationship between the central black hole and the galaxy they reside in, right? So this was where we need these space-based observatories. And so shortly after the mid part of the 20th century, there was another Princeton astronomer, Lyman Spitzer, who came up with, or was not came up with, but was a strong proponent of having space-based telescopes. If we do observations from the ground, we got to deal with the atmosphere, right? And sometimes it's cloudy, which for optical astronomy means we can't observe. For radio astronomers, they don't care. But for optical astronomers, we can't have clouds. And of course, we put optical astronomers on summits of mountains because we want to get above as much of the atmosphere as we can, because the way the atmosphere bends light, distorts light that we get from cosmic sources doesn't allow us to see very clear at the center. So, of course, the Hubble Space Telescope, HST, you all know of, right? Launched in 1990, as I said, still in space, temporarily shut down, but hope it'll be back doing science soon. Hubble Space Telescope, 1990, worked in the visible part of the light spectrum. Another part of the story that existed for much of the 20th century is while we knew cosmic sources emitted in the radio, remember that radio survey done at Cambridge, right? We knew about the radio sky, but you have astronomers work in the radio, maybe astronomers work in the optical part. The term that I remember learning when I was a student was that it was wavelength chauvinism, right? You picked the wavelength and then you stuck at that wavelength and you thought that was all you needed to know. But of course, 21st century science means you have to marshal all the evidence. You can't stick at one wavelength. And so what we have now are these fantastic fleet of observatories, two of them no longer existing, but they did for a time, that we can now use in concert. You have to marshal all of the electromagnetic energy, radiation we receive, and put all these pieces of the jigsaw puzzle together to figure it out. So what's this thing? SIRTIF, I like this name because it again tells you the acronyms that we often use. It's the Space Infrared Telescope Facility. Space Infrared Telescope Facility. When it was launched and it was successfully deployed, it was renamed in orbit to call the Spitzer Space Telescope, named after the Princeton astronomer Lyman Spitzer. Hubble, of course, named after Edwin Hubble. Chandra, which is that X-ray facility, also launched in 1999, July 1999, aboard the space shuttle, was the facility I spent 5 years as part of the science and mission operations team. It's operated by the Smithsonian Astrophysical Observatory in Cambridge, Mass, still doing fantastic, exquisite, high energy studies of the cosmos in the X-ray part. And then CGRO is the Compton Gamma Ray Observatory. This was the first great observatory that NASA launched. And it worked in the gamma ray portion of the electromagnetic spectrum. It's no longer operating. It's in the bottom of the Pacific. NASA intentionally did that. Once it ran out of its fuel supply, it was a large spacecraft where if they didn't intentionally put it in the Pacific, it had the potential to re-enter the Earth's atmosphere and maybe come and land over an inhabited portion of the Earth's surface and cause damage. We could have that happen. So NASA intentionally, at the end of its mission, put it on its orbit where it would enter the Earth's atmosphere and hit the Pacific Ocean and not cause any harmful consequences, but it's no longer operational. There are other gamma ray and high energy facilities operating, like Integral, which I'll mention if there's time. But this was NASA's idea of having this suite of great observatories that spanned the electromagnetic spectrum. And that has been the game changer in finding finding black holes. Now, focusing X-rays, which is what Chandra, I didn't tell you why the name. Chandra is named after an Indian-American astronomer named Subrahmanyan Chandrasekhar. Chandrasekhar, long Indian last name, a lot of consonants. His last name was often abbreviated Chandra, and that's what his friends called him, and that's what the telescope was named after. Subrahmanyan Chandrasekhar was a graduate student at Cambridge in England. And unlike now, where you can just get on a plane and 5 hours, you'll be on the other side of the Atlantic. When he was an Indian by nationality, he took a boat from India to England, and that was a month-long journey. And that time at sea, young graduate student, entering graduate student, he was playing with Einstein's equations, and he was the first to show that black holes were a consequence of GR. So it was won a Nobel Prize for his seminal contributions. And so he was honored by having the X-ray facility named after him, the Chandra X-ray Observatory. But X-rays are very energetic. Here's an optical telescope that you might get to use, or you might have to look at the moon, or there's 4 moons of Jupiter, the Galilean moons, right? You have this big piece of glass that collects photons, particles of light. You can't do this with X-rays. These are so energetic, you're not going to focus it. So kind of like when you were a kid and you went to the beach or you went to a pond and you took a stone and you tried skipping stones, right, on the surface of the water, that's what Chandra does. It instead takes these X-ray photons, and rather than having a piece of glass perpendicular to the entry point, uses something called Grazing incidence telescopes. These are the skipping stones. So rather than the mirrors being perpendicular, it's almost parallel, not completely because you need to focus them, and it gently curves these X-ray photons. This means that the facilities, the focal length are very big. This is about 10 meters between where the mirrors are to where the CCD, the device, no different than the kind of technology in your smartphone that takes pictures. The CCD here, the little imaging part, is no bigger than the size of your thumbnail, right? So the engineering of this always amazes me. You've got a 10-meter focal length. You've got 4 nested high grazing incidence mirrors to focus these telescopes, all to collect light on a device the size of your thumbnail. And there's 10 CCDs on Chandra that can be used. These supermassive black holes, we find them now at every epoch in the history of the universe. Very soon after Chandra launched, this was a paper I was lucky to be a part of with my actual supervisor at SAO. We published a paper. This looks unspectacular, it's just a bright object, but this is a black hole, a supermassive black hole at the center of a galaxy. Of course, we can't see the galactic light because this is at a redshift of 6. Now, that doesn't mean anything to you, but if we convert it to an age, this is an object that was producing the radiation we see for supermassive black holes about 1 billion years, just less than 1 billion years after the Big Bang. You might know the universe is 13.8, and that decimal is important because that's the precision to which we know the age of the Big Bang and of the universe. We know to that decimal point. When I was your age, the age of the universe was unknown by a factor of 2. There was a group of astronomers that thought the age of the universe was about 7 billion years, and there was another group of astronomers that thought the age of the universe was about 14 billion years. And it created all kinds of problems because the oldest stars suggested an old age, but there was other lines of evidence that these astronomers were pointing to that suggested a younger age. Today, of course, because we looked at the microwave background, that's another smoking gun, piece of evidence for the Big Bang, tells us the age of the universe is 13.8. So this very early after the Big Bang form has tremendous consequences for how we see structure, how we see galaxies forming right after the birth of our universe. It suggests that galaxies formed right away, and these supermassive black holes also formed right away. The mass of this supermassive black hole in this object the object was found with the Sloan Digital Sky Survey, which we then followed up with X-rays, is about a few billion times the mass of the sun. That's a big problem. At the time when this paper came out in 2004, it was not clear how structures that big, a few billion times the mass of the sun, could have formed so quickly, so early after the Big Bang. But as I said, theoretical physicists are very clever, and so they've come up with ideas that are still being explored. But the most important thing I want you to walk away from this picture is we see now evidence for this kind of activity at all stages in the universe. The question of how we find them in large abundance also comes back to X-ray. And what I want you to do now, it's kind of for you to wake up, is take your hands, right? And then smack them together. And then rub them. Slowly, gently, but rub them. What do you feel? Heat? Right? Should feel gentle warm. All right, put your palms back up. Let them cool down a bit. Smack them together. And now rub them at the speed of light or near the speed of light. Okay, you can't go at the speed of light or even near the speed of light. But as you go faster, you should have noticed, right? You must have felt more heat, right? Well, if you understood that, you're going to understand this picture. Because what you're seeing here is not the black hole. Because how do you see something that's black and around, right? What we're seeing here instead is something called the accretion disk. It's that pancake of material that swirls around the black hole, whose inevitable fate is to fall in. Remember this morning you took a shower, right? The water fell and it went towards the drain. It didn't fall directly in, right? The water didn't fall directly into the drain. It swirled around. You have to lose that angular momentum, right? And the same thing is true for these things. What you're seeing in this picture might look at like one of the Hubble deep fields. You might have seen these beautiful deep images from the Hubble Space Telescope. These are X-rays, and 80% of the sources you're seeing here are supermassive black holes. The other 20% are neutron stars, white dwarfs, these other things that put up X-rays, but most of these are supermassive black holes. And this field of view is about the size of the full moon. So it's not a very large survey, but it was something that we spent 250,000 seconds of Chandra pointing at a blank area sky, and we find it's littered with black holes. The reason why this was also tremendously exciting is because now we can follow up each of these detections that we see in Chandra with optical surveys. And we find that they're associated with bright galaxies, that the center of the galaxy, again, consistent with that picture. But a lot of these sources were identified with galaxies that heretofore, prior to this, didn't have any kind of evidence that they hosted supermassive black holes. Again, telling you why X-rays and higher energy astrophysics in particular are really important, because this allows you to find these extreme physics objects, these black holes, because they're betrayed in these high energies, gamma rays and X-rays in particular. So now you can start doing studies with them. Okay, this part is quick. I'm gonna wrap up so we can get to your questions. Why do you care if you're just interested in evolution of galaxies, or maybe just evolution of the universe with time? Well, this thing has started to become a little bit of a cottage industry. I'll start with this right image. I just took it from a paper, so you're actually seeing literature, graphs that are published by scientists, by astronomers in the literature. And what this is showing, again, let me move my picture bar away, is you can see here on the x-axis is redshift. This is the proxy that astronomers use to convey look back, how far away these things are. And remember, redshift to 6 is about 1 billion years after the Big Bang. So that's the way to keep in mind. And what you see is that the stars, if you ask the question, when do stars, is there a peak time in the history of the universe when stars are being formed, or are stars always being formed? Is it just we see stars being formed at the same rate at all times for the history of the universe? This picture suggests otherwise. Stars were not formed at the same rate all the time. As you might imagine, those early galaxies formed, those early structures formed, and then stars started forming. And it peaks at about a redshift of 1.4. And then as we go to now, excuse me, I'm going the other way. As we go to now, right, star formation has fallen down. Redshift is 0 today, is where we are. So apologize, it's going the back way. So this is early universe. This is today. And so it peaks at about 1.4. And then today, star formation seems to have been declining. If we look at the activity as measured by supermassive black holes, they follow the same kind of curve. They peak when stars were forming. They drop off as stars were falling. The star formation rate was dropping. So this suggests that there's an intimate relationship between the rate at which galaxies form stars and when these supermassive black holes are active. Why should one know about the other? Why should one care about the other, right? This suggests that there is a connection. Now in science, you always have to be careful, right? Even though there's a correlation, it doesn't mean that A causes B. Science you can kind of think of as looking at understanding the cause and effect relationship that we observe. This is a correlation. Doesn't mean it's causally connected. It just suggests there may be a connection. But if there is a connection, why? What is going on? Is this a critical ingredient for how galaxies form? More surprisingly, is if you ask the question, the x-axis, just think of the mass of the galaxy. Don't worry about these other things. The mass of the galaxy, how big a galaxy is on the x, and then how big the black hole is on the y. And this is also surprising. It tells you again that these are correlated. The larger the galaxy, the larger the black hole. The smaller the galaxy, the smaller the black hole. This again is a profound truth that we don't terribly understand. Why should something that resides in the very core, that has a region of influence not very big, have consequences? Our galaxy is about 100 light years in radius, right? How can it have influence over larger scales? This correlation suggests that these things are related. The size of a galaxy is related to the size of a black hole. So if you're going to a computer and writing a numerical simulation code that you put all the physics in, you want to see if you can get the universe coming out of your numerical simulation, you need this recipe, you need this ingredient in that recipe. Why? We don't know. Still trying to figure it out. The other part, and I'll do this really quickly because this comes back to something called the X-ray background. That was really the big part of my PhD thesis and why we needed to do the survey. The cosmic microwave background, the CMB as it's called, cosmic microwave background, I remind you, is the smoking gun, right? It's the experiment that Penzias and Wilson at Bell Labs had found with their facility. And it was understood very quickly by astronomers at Princeton when Penzias and Wilson gave their talk, gave a colloquium, that this had to be the leftover radiation, the leftover relic radiation from the Big Bang. But it's not the only kind of background we see. We can break it up into the optical part where we see another peak. That's due to stars. All the stars, imagine all the light coming from stars, they leave a contribution to the optical background. There's an infrared background. There's probably stars, AGN we think contribute. But there was also one found, in fact, the X-ray background predates the microwave background by 2 years, meaning the X-ray background was found first before the microwave. The microwave background, I remind you, we understand. 2 Nobel Prizes have been awarded now for understanding this. The X-ray background was poorly understood. It was not clear. It wasn't stars. It's not the Big Bang. What is this bump? What is this peak? What is it coming from? What produces this X-ray light? I'm going to skip all this just to go to, I'm going to go to this image because I know we're running short of time. What we did with this survey was we were able to look at by using X-rays, we were able to find large populations. And as you might imagine, because of this line of sight, it's just completely accidental to how we observe them, we find some sources that are completely edge on. So that donut, that obscuring torus, blocks the central black hole. There are some where it's, there's an angle that we have to the central part, but there's still a torus that we can see. These are called partially absorbed or partially obscured. And then, of course, we look right down the barrel of the gun where we can see the jet, or we can see the accretion disk and the central engine. And these are these unabsorbed. Well, we know these relative fractions from these surveys we've done. And by putting the fractions we see and the amount of radiation, that's what these 3 lines, I'll talk about the blue here. The blue is one from the contributions from AGN, active galactic nuclei, supermassive black holes that reside in galaxies that are not blocked. The red is where it is blocked by the torus. And then what we've had to put in to explain this peak is that there is a population of black holes that are so obscured, we can't see them in Chandra or XMM, the European equivalent. XMM Noon is a similar X-ray telescope to Chandra run by the European Space Agency, that you don't see these in Chandra surveys or XMM Noon surveys at all. The column, the amount of material is so deep, so large that it blocks the radiation altogether. But we can only fit the X-ray background by suggesting that there is a population of black holes that have been missed by these surveys because they're so obscured. Now, I told you that a critical part of science is not just coming up with the model, it's coming up with the prediction. So the prediction we came up with is to show that, we're looking at only the very bright end, because these Integral, which is the International Gamma Ray Astrophysics Lab, the successor to the Compton Gamma Ray, if you will. EXIST was a Harvard-led study that didn't get funding, so ignore this. NuSTAR is a high-energy facility run by Caltech, doing great science, actually did get funding, actually launched, still doing fantastic science. So we made predictions down to where NuSTAR could see in deep surveys, if we're right, if our model is right, this is the line that the survey should follow. So we predict NuSTAR should see a lot of these very obscured black holes. We might be right, we're probably wrong, but if we're wrong, we're going to learn something. But this was a prediction we made, and time will tell if we were right. The other critical thing that was facilitated, coming back to this question for why you should care, by having large samples of galaxies detected at high energy, at X-rays and gamma rays, we can now look at what galaxies they reside in. And one of the things that's come on in the last decade in terms of galaxies, remember I told you this idea of a Hubble tuning fork is not a good idea because it's a wrong model, because it misses the regulars. Instead, think of the galaxy distribution as these star forming and red and dead. And so these, they're called the blue cloud because these are the star forming galaxies. They're down here. The red and dead elliptical galaxies are up here. Look where these X-ray selected galaxies are. They're not up here. I mean, there's some, but for the most part, they're not there. There's some down here in star forming spiral galaxies, but not a lot. They're mostly in the middle. This again suggests that there's a connection between the role of the supermassive black hole in the middle to take the star-forming spiral disk galaxies that turn them into elliptical. There's a relationship there that's still being explored. But this was a really exciting discovery that I and a colleague published when I was a grad student at Yale that has real implications for how galaxies evolve with time. Okay, so I know I went a little bit over time, but I want to give time for your questions. I'm going to stop there. So the takeaway points that I want you to take away before we look at your questions, right? Black holes exist, without a doubt. So this idea when I was your age that it was still circumstantial, the theoretical physicists will come up with some other clever idea that will make the need for them moot, not true. They exist, and your counter argument, if anyone tells you that, is to say, and to point out Andrea Ghez and Reinhard Genzel and the Nobel Prize they won in 2020. Galaxies that host supermassive black holes that are active seem to have consequences for how they evolve. Outstanding questions for why there is a relationship. We don't really, we have ideas, right? Scientists always have ideas. They're being explored, but for the large part, it's still not well understood. The recipe, for someone who's paying attention, I told you how we can form black holes that are about stellar mass, a few, 10, 100, maybe even 1,000 times the mass of the sun. The black holes I'm talking about, these supermassive ones that look at the centers of galaxy, are millions to a billions times the mass of the sun. We have no first principles method of going to a blackboard or whiteboard now, and like we were doing with stellar mass black holes, showing you how they exist, there's no first principles argument that I can show you for how we get these black holes so large, the behemoth sizes that we met. Again, we have ideas, but this is an outstanding area of astrophysics. How do black holes that probably start off as remnants of stellar evolution, how do they quickly grow? And how do they form, how do they move towards the centers of galaxies where we sit them now, right? These are great questions, still being unexplored, and these are areas that you can contribute to. And of course, the last thing, even if you don't care about black holes, even if you don't care about the extreme gravity or GR, or any of these things we talked about at the beginning, if you want to understand how galaxies evolved, how they change with time, and how they change from spiral to elliptical, this tells you you need to worry about these black holes. So I'm going to stop there, but I'm going to go to your questions. Let's go to, oh, let's see if that'll work. Okay, and I'm also going to see, let's see, can black holes theoretically be formed without stars, meaning without the mass of star? Great question. I'm just going to read these quickly, and then I want to stop sharing because I can see you guys and you can see me. Can planets orbit black holes? Say if the sun were replaced with the same size, I'm guessing life would end, but would the planets still orbit? What leads to type 2? Okay. Okay, here's what I'm going to do this, because I can look at it on my phone. So I'm going to switch to this presentation. I'm going to stop sharing so I can bring you guys out. And now we can have our conversation, the best part. All right, so the question about planets and around black holes, that's a great question. Now, one of the misconceptions that people often have when we talk about a black hole, I'm going to ask you this question. I should have put this maybe as an end clicker question. You know, if we replace the sun with a black hole of the same mass as the sun, so our sun weighs 2 × 10⁻³ kilograms. Imagine instead of a sun, so imagine instead of a star, we had a black hole that measured 2 × 10⁻³ kilogram. Do we get sucked in? Let's see if I can do, well, thumbs up, we can do this way. Thumbs up if you think this our Earth gets sucked in. So the question I'm asking you, we change the sun to a black hole of the same mass. Does the Earth get sucked in? Yes or no? I see some no's, 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 no's. Okay, I think you guys are succumbing to peer pressure. Yes, all right, where's one brave person? Couple of yeses. Good, I like it. To me, the best clicker question is where you got confusion, because it tells me we can make progress, right? The worst clicker question, in my opinion, is where you get most people answering right, because it's a wasted question. So the answer is no. If it's this, because remember, the Earth goes around the sun because it's just obeying gravity. And if the mass is the same, that's why that caveat was so important. If we replace the sun with the mass, with the black hole of the same mass, the gravity doesn't change. The Earth will continue orbiting, just as it is now. As one of you pointed out in the Q&A, however, it has enormous consequences for life on Earth. We require the light and energy from our star for life to flourish on the third rock from it. So if we had a black hole, yeah, it'd be really cold. Life as we know it wouldn't exist. So it would have consequences for life on Earth and maybe the other places in the solar system where we think there might be good places for life as we know, or life, bacterial or microbial life right now, but it would have enormous consequences for life. So it's not that black holes are like these big vacuums that will suck everything in, right? It's only if you're close to it, that you're sufficiently close to it where it has the ability to pull you in. And this is a great point. I never defined the event horizon. That came up in one of your questions, right? We talked about the escape speed. You know, roughly 10 kilometers per second is what you need to launch something to escape the Earth, right? The event horizon is that boundary around the black hole where the escape speed identically equals the speed of light. Meaning if you're at the event horizon, you need to be moving at the speed of light to escape it, or greater, if you could. If you're beyond the event horizon, you can escape the black hole without having to go the speed of light. Inside of the event horizon, you would have to travel faster than c, which we can't do. Nope, it's a fundamental speed limit from Einstein's theory of special relativity. Nothing can do, right? So inside of a black hole, you can't escape it, and that's what defines that event horizon. There's nothing magical about that. There's no welcome to black hole sign or anything you would see. You would just notice that you can't escape it. The spaghettification, as one of you pointed out, has to do with the fact that the gravity around a black hole is so extreme. The pull of gravity at your feet, if you're falling feet first into a black hole, the amount of gravity tugging at your feet is much greater than the amount of gravity tugging on your head. So the spaghettification means you get stretched out like a piece of spaghetti. You get ripped apart. And you might think, well, this sounds incredibly like sci-fi. but these are called tidal disruption events. It's a vague term that really hides the spaghettification, but we actually have evidence of stars in our own galaxy in the Milky Way, downtown Milky Way, that get too close to our black hole and they've been torn apart. The black hole responds because it devours that material. It turns on and we see it. So stars get ripped apart. This has to do with, relates to a question that one of you asked, what causes a black hole to stay dormant? And that's a great question. That's why I called them monsters lurking in the dark, right? Black holes are only, their existence is only betrayed if they're eating, if they're feeding on the material that is falling into it. If they've exhausted their accretion disk, if there's no material swirling into it, it just sits there. But it doesn't give off any kind of electromagnetic radiation that we can observe right now to know that they're there. So these active black holes are the ones that we can see with X-ray telescopes like Chandra and XMM, but we think every galaxy has one. They're dormant. And if you ask, well, what's the fraction that are active versus dormant? This is where it depends on how you find them. When I was your age, it was thought to be a very small fraction, maybe 1 to a few percent of all galaxies had evidence. But because we know now, we've been missing a large fraction of galaxies that actually have actively accreting black holes, but have been blocked by these obscuring medium. That fraction maybe is about 25%, 20%, depending on the kind of survey. So a large fraction of galaxies seem to have evidence for actively accreting supermassive black hole. The inverse, the corollary, is also true, right? Most galaxies have dormant black holes until something falls in, until it collides with another galaxy. Galaxies, you might ask, well, how do we get Milky Way so big? They could form in situ, they could form massive, and some may have done early in the history of the universe, but for the most part, they grow by mergers. It's a violent universe. These galaxies cannibalize each other. In fact, the Milky Way is in the process of cannibalizing smaller galaxies. If you've been to the southern hemisphere, you might have seen the Magellanic Clouds, the large and small. They don't look like a spiral or elliptical. They're small galaxies, but they're in the process of being ripped apart by the Milky Way. They're falling in on the Milky Way. And so galaxies form by this process. And that's how we think these supermassive black holes grow so big, and through these collisions and mergers sink towards the center, because that's where the large gravitational well would exist. Let's see, how much time do we have, Barb? Jody? Can we do one more question? 2 more questions?
Probably maybe 5 more minutes.
5 more minutes. Okay. So let's see.
Sorry, I was muted, but yeah, that's what I was saying.
That's fine. Okay, Macho. Okay, this is a great question. Macho is an acronym. Stands for Massive Compact Halo Object. The M and A come from massive. The compact is the C. Halo is the H. And O is object, macho. And so macho's almost 1990s, almost 30 years ago. This was probably one of the first ideas that astronomers came up with to explain what dark matter. You might know, you might have learned that the material that you and I and stars, the planets, the galaxy are made up of is a very small fraction of what makes up the universe. About 5% is the stuff that you and I and the things we can see. The rest of the universe, some 95%, is invisible. And because it's invisible, we use the word dark because we can't see it. And the invisible stuff comes in 2 forms. There's dark matter. So this is material inside of a galaxy. And in fact, this is a great one reason I want to take it, because this is another area where it was a pivotal female scientist that made enormous contributions. Her name is Vera Rubin. And in the 60s, she was looking at spiral galaxies, again, those disk galaxies that you can see the reservoir of gas and dust, and using Kepler's laws, exactly the kind of Kepler's laws, remember, that apply to our solar system, that apply to the dynamic of stars around downtown Milky Way. She was looking at structures in these spiral galaxies and noticed that they don't fall off with distance, which is what you would expect for things farther away. In fact, it seemed to grow with distance. This was one of the first pieces of evidence, observational evidence, for dark matter. And so a groups of astronomers suggested that what if there were these compact objects that reside in that halo. So remember, there's the disk, there's the bulge, which is kind of like the soccer ball in the center, and then the halo is that kind of three-dimensional large sphere that encompasses the disk and the bulge. And so what if there are these things that are very heavy, that we can't see very well, but maybe they can distort light around it and we can see their existence from it, and they were postulated. They were suggested to be what dark matter was. This has been studied, and the signature you would expect to see from the large population you would require to explain dark matter has not been seen in gravitational lensing. This is the idea that because you have a very massive object, light is bended, right? That was how Einstein's theory of general relativity was confirmed observationally. Remember, it was a solar eclipse in 1919, Sir Arthur Eddington did, that provided the evidence that the bending of light that they observed was exactly in concert, consistent with what Einstein predicted. So that experiment has been done. It doesn't seem as if machos are what dark matter is. Instead, the best explanation we have, again, circa 1:45 Eastern Time Friday, for what dark matter may be, which will change, is something called WIMPs. These are weakly interactive massive particles. I love these acronyms, right? So not macho, but WIMPs. And if you've studied or looked at particle physics, there's a whole zoology that has to do with the kind of subatomic world. And so WIMPs, weakly interacting massive particles, are thought to be these leftover material from maybe early part when the universe formed, where they don't respond to light, which is why we can't see them, but they respond to gravity. So the massive part is where the becomes critically important. Massive because they have weight, they could explain the dark matter, they respond to gravity, so they have implications. But weakly interacting, meaning we can't see. That's the best explanation, probably the most favored one if you talk to most astronomers for what dark matter may be, but we have no evidence. Right? So but there are experiments that are underway at underground mines around the world to look at, again, observational signatures for what if they are WIMPs, and they continue to operate, and they continue to make to refine what the mass could be. But to be honest, the real answer is we have no idea what dark matter is, what it's made up of. But we know it's there because, again, we see the signature by looking at spiral galaxies. Dark energy, which is some 70% of the universe, dark matter is the 25%. Dark energy is most of the universe, and we have no clue what it is. Dark energy was only discovered at the turn of the century with the Hubble Space Telescope. Again, it had to do with supernovae, type 2 supernovae. Remember, type 2 are these massive stars that explode. And so by looking at these supernovae that are used to measure cosmic distances, astronomers recognized, using data from the Hubble Space Telescope, that the universe is not only expanding, as Edwin Hubble discovered in the 1920s, the expansion is accelerating. The space between galaxies is not only increasing, it's accelerating in its expansion. And so the only way this could work is it had to be some kind of repulsive source that was causing that acceleration, and that's where the term dark energy came from. We have no idea what it is. 95% of the universe is dark matter and dark energy, and we have no idea what it is. So maybe I'll stop there, because I think for your generation, you guys can solve these problems and then tell me and tell us what they are as you pick up your Nobel Prize.
Awesome. Well, we sure thank you, Dr. Virani, for being with us and spending your time with us today. And I know that all the participants were looking forward to this, so I know they've enjoyed it. Yeah, we do have to stop here so that everyone can have a break before heading into their next whatever. For us, it's social block.
Can I just, sorry, Jody, can I just mention one other thing?
Of course.
Yeah, the one reason why I wanted to use Slido instead of the Q&A, because I just now looked at the chat and I see some of the questions from Cassie and so on, and I promise I will reply, is that the Q&A on Slido is going to be up for several days. I'm going to go back today and maybe tomorrow. That's how I'll spend my Saturday, and I'll answer all your questions. So if I didn't answer your question during our portion right now, it's not because it wasn't important or not interesting. I just had to pick easy ones that I could answer, not the harder ones. But I will go back and answer your question. So just keep that URL and you'll see your answer. You'll see my answer maybe to your question later this weekend.
That is really cool. Thank you so much. Okay, so I guess you guys are able to exit now, and we'll see you here in a few.
All right. Thank you again. And New Mexico Tech will see you at the top of the hour for your learning block. Thank you, everyone.
That was so fun.
Was that good? I don't know
Oh,
if
yeah.
was the level right? Was it too high?
No, I mean, I think it was fine. I know that they'll talk about it and they enjoyed it. What do you think, Cassie?
No, I think it was, yeah. I think it was
Yeah,
good.
I think
And
they
it was-
enjoyed it.
I think it was especially good because you talked about some of the topics that we heard about yesterday and